Area under a curve. Presentation by Brett Billingsley and Salahuddin Zaytoun. In this presentation, we're going to talk about how to calculate the area, but not any area. We're going to talk about how to calculate the area under a curve. But beginning, we have four problems that we need to mention. That the first one, how can we calculate the area under x power by 2 from x equals 0 to x equals 2 using Reimann approximation? And two, how can we use Reimann approximation to prove that the area of a triangle with the specific vertices is equivalent to the line y equal x minus 1? And three, how can we use the Reimann approximation to calculate the amount of work done when force is not constant, and how does it compare to when force is constant? And the same thing when the amount of distance traveled when speed is not constant, and how does it compare when speed is constant? So in the beginning, what is the Reimann approximation? The Reimann approximation is a technique in calculus for estimating the area under curve by summing up area of many small rectangles. Or we can talk about the area under the curve right here. Mathematical representation of approximation. So here we have two important keys that we need to talk about, which are the fx and the z. So the z is the end value minus the start value over the number of rectangles. And because we will have many rectangles, so we will use them as fx1, fx2, fx3. But I want to mention that when we use the left Reimann approximation, we do not use the fx end value. And when we use the right Reimann approximation, we do not use the start value. And the first example that we're gonna show you guys today, we have the mean approximation limits to the domain 0, 1. And this example right here, we will talk about math behind proving that triangle and y equal 1 minus z. So in order to find the total value, we will need to time the fx times z. And we have the fx here but in 0.666 and 0.333, and the z is 1 over 3, as we have three rectangles right here, and it's going to be 1 over 3. So 0.666 times 1 over 3, so we're going to have 0.22. And also when 0.33 times 1 over 3, we're going to have 0.111. And in the total, we're going to have the total area is going to be 0.3333. And as we move here to the most important, one of the important parts in the project, we have estimating the area underneath x power by 2. So in the first example, when we have 2 rectangles and 4 and 8, and we're gonna have 16, 32, 64. The z in the first one gonna equal to 1, and the second one gonna equal to 0.5, and the third one gonna equal to 0.225, equal to 0.25. And the reason is because we got two moves over 2, so the first one gonna be 1, and the second one gonna be half because 2 over 4, and the third one gonna be 2 over 8, and the fourth one is gonna be 2 over 16. So the first one the value of it is 0, so we will have only the value of one of them, which is 1 power by 2 times 1, which is 1, and the second one we're gonna have 4 moves, so the first one gonna be 0, the second one gonna be half power by 2 times half, and the third one gonna be 1 power by 2 times half, and the last one 1.5 power by 2 times half, and the total of this is gonna be 1.75. And in the 8 rectangles we will have the same thing, we will have 8 moves, and the value of z gonna be 0.25, and the area gonna be 2.1875. And in the example of 16 and 32 and 64, the value of z gonna be here 1.155, and here and in the 32 example gonna be 0.0625, and the last one is gonna be 0.03125, where we gonna time the value of z after we do the x power by 2, and then we need to add all the values together to get the total area from each one of them.
So once we add up all of our values, we get a total area of 2.4218 for 6 left rectangles, 16. And then for 32, we get approximately 2.54 as the total area. And then for 64, we get approximately 2.60. Now, one thing I would like to note is when we have continued right here, that means there are more values that are needed to be added up, but they wouldn't all fit on this PowerPoint. If you would like to look at all those values, you can go ahead and look at the appendix of the final report. And this applies for the rest of the presentation as well. All these continued values are inside that report. So if we move on to the graphs, we could see here, graphs of x squared, we have our 2 rectangles, one right down here and one right here. 4 rectangles, one down here at 0, 2, 3, 4. 8 rectangles right here. We could see that our area is getting bigger and bigger. And then with our 16 rectangles, we have them right here, 32, 64. One thing I'd like to note is that sure, they're increasing the area, but it's slowly closing the gap because it is an approximation. So a key takeaway from this example is that how the Riemann approximation relates to the true area of x squared. So the true area of x squared underneath the curve is 8/3, or approximately 2.66, between the values of 0 and 2. And if we look back even at our 64 rectangle example, we could see it starts to sort of even out there, but the only reason it's not as close is because of all these little gaps, because it is just an approximation. But it is getting closer and closer the more you add rectangles. So the more rectangles there are, the closer you're going to get to your final answer. Now let's begin with the first real world application of work. The formula for work is force times distance, and usually this is easy to calculate when your force is a constant, like I'm applying 100 newtons of force every second. That's just 100 times x, whatever your distance is. And x is usually the changing variable. But we're going to compare work equals 100 times distance, because force would be 100. We're going to compare the area of that with the area of force not being constant, which our equation for force in that case would be 100 plus 10x plus 0.5x squared, and then that's going to be multiplied by our distance of x. So you're going to end up with the equation work equals 100x plus 10x squared plus 0.5x cubed. Now for this application, we'll be using the left rectangle method to calculate the area underneath the domain of 0 to 15. The reason that 15 is in parentheses is because we don't include the end value with the left approximation. So if we look at our chart, this is for work if it's a constant of 100. We see we have our rectangles. We're going for 30 rectangles because we're going to use the domain 0 to 15 with 0.5 second intervals in between each, which can be seen right here. And then function evaluation is all the areas of the rectangles. And then for work not being constant, we have 0.5, and our function evaluation gets a bit more messy, and then we'll end up with a total area of 15,655 as opposed to the total area of 10,875. And then if you need a graphical representation of constant and inconstant force, We could see this is linear, so we have a nice even number, but this one right here is not. All right, so our next real world example is going to be area under a distance curve. So distance is usually calculated by multiplying speed by time. And in some cases, in more easily calculated cases, speed is a constant for and for this we'll be seeing what happens if speed is not constant. So for the constant that we'll be comparing it to, we'll be using speed at 45 miles an hour. And then as a non-constant, we'll be using t, or we'll be using 6t plus 0.1t cubed as our speed, and then t being time. So this is going to end up being 6t squared plus 0.1t to the fourth degree. In this example, we'll use left's rectangle approximation, so we'll be excluding 10, but the domain is 0 to 10. Now for a distance of 45, for a 45 constant speed distance, we'll get a total area under the curve of 21,000 or 2,137.5 miles. And then all the math is right here if you need to look at it. With function evaluations, number of rectangles, we're using 20 rectangles so we can have a z value of 0.5 so we can get a semi more accurate answer. And then for distance of t against 6t plus 0.16t cubed, we're going to have approximately 3,610.8 miles. And also using the same z value, same number of rectangles. And for the graphs of these, we can see here, this one, is the constant is linear, the inconstant is definitely not. And we could see that the inconstant value is also greater. So the notable thing for real world examples is that when the constants are not constant, you get more work and more distance. And for approximating what that work and distance is, you can use Riemann's approximation, but for more advanced mathematicians, I would just suggest using integrals. And that ends our slideshow. Thank you for listening to the presentation.